Thanks, Yuan. I'm Jin Peng Liu. I graduated from Maryland. I'm currently a postdoc at the Berkeley and MIT. Also, one of my supervisors, Lin's here, and I will be joining in Tsinghua as an assistant professor, and in the next summer. So today I would like to share my recent thoughts on moving towards probably efficient quantum algorithms for solving certain nonlinear dynamics, as well as for some contribute to the large-scale machine learning models. So here is the two parts of my talk, and for the first part, I will try to review some progress of solving nonlinear differential equations, also with some recent updates. And secondly, I will talk about how to design some efficient quantum gradient descent algorithms toward the training process of some machine learning models. So I think, and during the whole week of, I think during the workshop, and we are pretty great to hear a lot of exciting progress from the algorithm part, and also with some contributions from the applied math, also from scientific computations, and many pretty fantastic ideas contribute to the design of the quantum computations. And so here, there are some pictures I would like to share about the current quantum device we have, like to contribute by IonQ and by the IPAM, by Google, etc. So we are making strong efforts in building more and more powerful quantum device in order to in the future, in order to really build some fault-tolerant quantum computers. Last feature is another current device we have, but it's just in our imagination. So it's a movie, the so-called Wandering Outsiders. It's a Chinese movie this year. So in that movie, we really try to imagine if we have a super powerful, intelligent quantum computers, and we may have a chance to really do a lot of things, like really anticipate the future, even change the futures. So we really have such a confidence that if we have such a powerful quantum computers, we can really make the most powerful device in human beings histories. This is because we really have some strong evidence to support our confidence, like the many problems that we have some guarantee that have some potential exponential speed up for certain problems. Like I just try to pick out some standout examples, like the integer factoring, and which is the NP problems. But we know there's a sure algorithm which can achieve the polynomial type to solve the problems. We also have a bunch of examples rising many-body quantum physics, and as covered by a lot of talks during this week, that people really try to introduce a lot of the problems we may design some efficient quantum simulation algorithms and with some potential speedups. And finally, we are hearing a lot of the exciting progress about how to design the quantum numerical linear algebra algorithms in order to really target for some certain classical problems and in a certain quantum reformulations. So there are some results that we may know there are some potential even exponential speedup might be possible. And we expect that maybe in the future, can we really achieve some quantum revolution for some certain killer apps? Can we really use a potential quantum algorithm in future to work on some the cutting edge problems and techniques that we really care about? So if we really ask everyone in our society, what's the most the concerning problems that we care about, I believe there's a bunch of problems can put it on our list, but I really pick up something that when people care about right now, and maybe many people will really vote for that. So, for instance, we care about how to model the pandemic spreading, how to govern the change of the climates and atmospheres, etc., and how to design efficient training process towards some large language models, fundamental models, etc. And so I believe there are a bunch of the examples for the sort of large-scale computational models that we want to target for. So if we have the most powerful computer device and in the future, and we need to think about how to target for the most significant problems we want to solve about, like these examples. So in order to really make strong effort moving forward to that, I believe there are many essential challenges we should think about. And here I'm trying to talk about two of them. So one is the fundamental gaps between the linearity of quantum mechanics, which is the fundamentals of the quantum computations, towards the nonlinearities of many real-world systems or models we care about. So nonlinearity is one of the challenges. The other case, we can just briefly call the end-to-end. That means how to design some end-to-end approach to efficiently interface the quantum between the quantum class of data. So, I mean, how to efficiently upload your data, how to efficiently download your data, and really try to get a better communications between the quantum computers and classical or worse. So there are two essential challenges. So this is relevant to my research agenda. Maybe I will try to put all of my, try to devote my research to these, the terms of so-called quantum for science. So that means that we do not only do something for the quantum, but we also try to do something more relevant to the scientific computation or scientific discovery problems. And so you can see in this agenda, so we not only care about like many problems arising from the quantum physics, from the quantum simulation or quantum linear algebra, we also care about how to efficiently solve some OD or PDEs arising from natural science, how to really model the epidemics or flus. And in the data science, we also care about how to really improve the current state of the art algorithms like gradient descent, or really how to put into practice and how to really do like sparse tuning. So I will try to cover these contexts. So there are some very brief reviews, and like maybe many of you guys have already know that, so or even know better of me, but just try to maybe I can really do some really quick recaps. So I think all the capability of simulating the certain dynamics coming from the result of efficiently simulating some quantum physics. That means how to efficiently do some quantum simulations. So here is the basic description. I mean, we can really describe some sparse Hamiltonian systems where we assume the sparsity n is much smaller than the dimensionality n. S is smaller than dimensionality n, and then so given a certain distribution of the initial value problems, we aim to design efficient quantum algorithm in order to produce an estimate of the final states. So in the quantum algorithms part, and that means we need to decouple and really design a sequence of the local quantum gates, like the U1, U2 multiplying up to UK as a product in order to approximate your maybe the exponential propagators like the e to minus IHT or more complicated case. So, and as shown by many pioneers from Sasloy, Barry, Lawrence Chang, and many results, we know that currently the state of the art, the capacity of simulating sparse Hamiltonian can achieve such capacity like linear in terms of the sparsity as well as evolution time, and also it can achieve a polylogarithm in terms of the dimensionality of your whole vectors. Also it can achieve high precision, I mean polylogarithms of 1 of epsilon. Also, we know a bunch of applications and can be appearing like in rising from like the quantum physics, quantum chemistry, and all. And so we move forward to from the quantum physics to the more general linear algebra case, and one standout result is for solving a linear system inside the quantum computers. I mean, we also need to have some descriptions of the sparse linear system. The description means that you may have protein coding or some sparse matrix sections, and that has been covered by many talks. So if we have such descriptions, and we want to produce a quantum encoding of the solutions proportion to the solution of your linear systems, and we know that so that's we can have such a capacity of solving a problem like linear in terms of sparsity and linear in terms of the condition number, and also achieve a potential the speed up in terms of n, because we can have the polylogarithm in terms of n capacity. Also, it can be generalized to many linear algebra problems as we introduced during many talks. And so right now we can also move forward to look at some continuing problems, like we can consider, similarly we can consider some distribution of the sparse linear ODE problems, and our goal is to really produce a quantum encoding of the solutions. We know that for this standard ODE, and there are many results like starting from Berkeley and also other, all of us try to really design some efficient quantum algorithms for solving linear ODE problems with the complexity is very similar as the Hamiltonian simulation to achieve a potential polylogarithm in terms of n. We also know that a bunch of applications like from the PDEs and from open quantum systems. We also study like fast forwarding and lower bound results. And so for many of the results, and I would say at this moment, we have some better understanding of really how to target for these linear problems. So I would like to target this should be certain different levels, and maybe by Lin's word, Lin would like to target the hierarchies of the structures, but I would like to target a trilogy of the quantum computations. From the first level, or the easiest level, it's natural to simulate the quantum or unitary dynamics in some sense, like maybe it has more formal distributions, but right now we just call it natures. The second level, and usually if we really want to simulate some linear and no quantum dynamics, usually no unitary, and we need to take some actual efforts, and actual means sometimes easier, sometimes hard, sometimes affordable, sometimes not, and so usually we should need to really consider some actual design like linear combinations of unitary, linear combinations of Hamiltonian simulations as we did by Zhong and Lin, and together with me, and so there are many ways to really do it and do that problems. But finally, on third level, even after we have a fault-tolerant quantum computer, it's still hard. It's exponentially expensive to really simulate some strong nonlinear dynamics, and I would say it's a long-standing problem. So if we really try to decouple the hierarchical, and maybe many of the problems can be achieved even like by simulation-based algorithm, and some problems that we can achieve and by some actual advanced techniques. But finally, we really found it was a long-term standing on open problems that people really understand, try to gradually understand how to do that, and at this moment, but still we feel really hard. But really need to go high, really need to try to consider how to do that, because if we really want to solve some fundamental and cutting-edge problems, like as we mentioned, like climates and the pandemics and the language models, we really need to consider what's the limit that we can do. We need to go high. So that is our target. So it was a long-term standing open problem, and maybe it's not a fair statement, but I would like to say it's because right now we know at least how to solve some problems and partially, but we cannot solve all of them. So from this side, I would like to cover some aspects about describing hardness. I mean, why nonlinearity is difficult and even more difficult than the classical computing. And so one reason is about the design of the efficient quantum algorithms. And so if we really look at as Konstantina mentioned, the earlier paper by Lenz and Osborne, so they consider a straightforward design of simulating nonlinear dynamics by using multiple copies. That means they use the tensor products of different states in order to represent some high-order couplings. But however, throughout the algorithms, and we need to maintain all the copies, and in order to simulate the system, and each time we need to get rid of many of them during iteration. This is because in the binomial calling theory, we are not allowed to know the information of some unknown quantum states during the computations and process. So, and at that time, we don't know how to do. We didn't know how to do this. And on the other side, and we know a bunch of lower bound results, and even earlier, like from 1998, and also a bunch of results, we know the nonlinear can imply some really unlikely results like so if we have a efficient quantum algorithm to solving some general nonlinearity problems, that can directly indicate some polynomial time solution for Sharpe and p-space problems. If you do not know that, maybe just simply say they are all NP hardclass. And so it sounds like the nonlinear quantum computation sounds not like the real computation capability that we can achieve in our real worlds. So from the linearity of quantum mechanics, maybe we can only try to solve most of a linear problem and only try to target for some specific design of a nonlinear problems. So next, I'm trying to tell you how to really solve that. So this is the a paper that has been mentioned by Constantinos and in the earlier talk, and at that time we really tried to design a first efficient polynomial type quantum algorithm with potential speedup in terms of dimension n. So in order to solve a class of the so-called weighterly and dissipated nonlinear differential equations, I think maybe it's better to really quote some words by some other senior researchers like Andrew, and try to really introduce the results and just recently and about the meaning. That means try to really, at that time, we try to, together with many guys like Harry and Herman, Harry, and Nuno, Constantino, and Andrew, and we really designed algorithms that exponentially improve over the best algorithm in 15 years. Also, another maybe a better appropriate distribution of algorithms was contributed by John Pascal, and he said that on Twitter, really, he said that so while there are significant steps that are still among the first in creating nonlinear systems, and more researchers will likely analysis refine each method, and even before the hardware needed to implement them become reality. So yeah, I totally agree with John's opinion, because we really do that, because there are a bunch of different researchers try to conduct fine-grained study of different methods. So I use this slide to really summarize and what we have done and in recent years. And so these classifications was contributed by Professor Shi Jin, and he tried to call a large class of methods, including Kalman or a special Kuhlmann or some other methods, as a linear approximation approach. In this first approach, and the basic idea is that we try to find some way to linearize or embed your n-dimensional linear ODE system into a polynomial size n-dimensional linear ODEs. Usually we need some truncations in the general case. And the tolerance is to control the truncation error, because we know we need to guarantee why the linearization should be an effective approximation toward the original nonlinear systems. On the other side, and there are many other researchers focusing on the sort of phase-space representation. That means how to design some Liouville or Kuhlmann or Leverset or many other approach in order to really embed your system in a larger phase space, but without truncation. So sometimes with better representation, because you do not really lose the information. However, you need a exponentially large space. That means when you really encode like a dimensional ODEs onto a real space n-dimensional linear PDEs, that means you need the exponentially large degrees of freedoms, and usually it's hard to obtain exponential quantum speedup from that way. So that's the reasons that I try to choose the first way. For the rest of the talk, I still try to develop column linearizations and how to really achieve a potential speedup. But all the harness is to understand how well we can approximate the problem with. So so there are some technical parts, and thanks to the Constantina, so I do not really need to dive into them to tell people know what it is, because something I think people has really know from the earlier talk. So at the beginning in our earlier paper, we focused on a standard quadratic system by as certain formation as this form, and we just informally speaking, we hope the linear measure should be dissipative, and so that means we have some definition of like all the real parts of item value should be strictly negative, and one example is the Berkeley equations, and so under some proper boundary condition, like D-Hay boundary conditions, and if you don't know the Berkeley equation, just for simplicity, it's a simple form of the one-dimensional Navier-Stokes equation in some sense. So given some distribution of your nonlinear problems, we also need to characterize how strong the nonlinearity should be this. And so we define such a parameter R. Informally, sometimes we would like to call the quantum Reynolds number, but it's not exactly Reynolds numbers. It's inspired by that. And so we use that to really characterize the ratios between nonlinear and inhomogeneous strings relevant to linear dissipations. I will also need to mention that if you pick up different nonlinearities and really also pick up different error measurements, the forms of the parameter R can vary. The main results from one of our earliest papers is that so really devise this the first polynomial type quantum algorithms for creating the nonlinear problems and with potential exponential speedup. And so basically, if I is more than 1, and we know this is generates the solutions of like, because for all the problems we can use this quantum column linearization to linearize it and output a certain quantum state solution proportion to the solutions with such a complexity. I mean, polynomial time in terms of t and linear in terms of like the sparsity s, also quantity q corresponding to the details of your solution, also 1 over epsilon accuracy and polynomial n speed us. And there are some recent results like the Harry really try to improve your complexity to the linear t and polynomial 1 of epsilon under some a little bit different conditions. Also, some people like the paper by Dong'an and me and Jiasu, Stephen Jordan and Guanghao Lo, and we really try to develop some better conversion criteria towards some certain specific nonlinear PDEs. Also, I would also like to say that there are other recent progress in like the classical community, and we are glad to see at that time our state-of-the-art analysis of the column linearization has been applied to the classical nonlinear control and classical computational fluid dynamics. Some people really design some algorithms, or some people really use this approach to do some control analysis. So we are really glad to see we have some contribution even independent of quantum computation. Even we need to wait several years, long time to really have a powerful enough quantum computer to run a quantum algorithm. But before that, we are glad to see our classical algorithm has been applied to many discipline areas. So this is also a very informal, very quick recap of what we did and for the column linearizations. And for column linearization, so the basic idea is that we cannot use naive linearization, because if we only locally approximate some nonlinearities, and if the time is short, maybe it's okay, because we can really replace your nonlinear terms by the linear terms multiplying by your Jacobian matrix. So it's a few of the iterative methods that can be done, because you can update your Jacobian matrix. However, quantum is not allowable because of a no-coin quantum theory. So we cannot update your Jacobian matrix throughout your iterations. That's the reason that we cannot focus on the naive local linearization, but instead we need to turn our attention toward the global linearization, and maybe column linearization is one of the simplest way to do the sort of global linearizations. The basic idea is that for the first step, we need to embed your n-dimensional nonlinear ODEs and onto a infinity-dimensional linear ODEs in the infinity-dimensional Hilbert space. The second step is to do a proper truncation. We need to guarantee the size is not too large. It should preserve the size on the poly of the n, and so our contributions in math is to really prove the convergence, and given the convergence the radius, and we try to really relate some fine grained some convergence conditions compared to earlier column linearization, but we achieved the best state-of-the-art analysis at that time. So the last part is that given a linearized ODEs, and we are able to develop some really efficient quantum algorithms and with complexity polylogicals in terms of n. So this importance about the size of the polynomial is also important to really guarantee that why is effective linearization, because we can really prove the convergence. So a simple example is for the linear case, you can see we just try to regard all the high order monomials as your new variables, and then we take the derivatives by the chain rules. It's not the 2u, right? It's when you need to 2u multiplying du of dt, so we have higher order terms. You will get higher and higher order terms, and anyway, you can increase your numbers of the observational variables, but you will also need to tolerate it's larger and larger systems, and finally when you cannot tolerate it anymore, and you need to do some truncations, like truncated by n, and then it will directly give you a certain linear ODs with new observable variables, and so we just use the yj responding to the u to the j. It's a simple 1D example, but you can imagine that we can really carry out such a procedure of linearization toward like the high dimension nonlinear ODE systems. That is what we did and in our previous papers. And on the other side, we know some lower bound results, and also it has been introduced by Constantina. But basically speaking, just we try to, at that time, we give one example under a condition 1i is larger than or equal to 3/2, and we shows that for these examples, any quantum cannot do better than the exponential time. So for that example, the base idea is really combine the two nice theoretical results. One is from theoretical computer science, the other is for math. From one result, it's very standard lower bound the procedures to prove something like this, because we know it's hard to distinguish two non-orthogonal quantum states. If they are close enough, have the large overlap, it's pretty hard to distinguish. On the other way, and we really make use of the butterfly effect of the nonlinear ODE system. The butterfly effect means the initial sensitivity. Actually, it's not equivalent to chaos, but it's just some of the chaos. So some necessary condition of chaos. The sensitivity means that a small initial divergence or initial error can result in large variations. So, and the base idea of all the proof is to try to design a amplifier protocol, and because we know the butterfly effect can really amplify your angle of the two potential states. So on the left-hand side, you have the two quantum states have small difference and how to distinguish. On the right-hand side, you have the two quantum states as output, but have large difference, easy to distinguish. And so you can see it's easy is hard, but it sounds like a contradiction because you can not really pass the amplifier. If you can easily really reduce a hard problem to an easy problem and really solve. But it's highly unlikely. People believe you cannot do it. So that's the reason that we can really use this contradiction to construct a certain lower bound to show that there's no polynomial type quantum algorithm can really close the gap, can really try to pass the amplifier in polynomial types. So, and we give such a proof, and it can also be generalized to the proof of solving other problems, even beyond ODE problems, and it can really be used to really understand like the state discrimination problems and any other problems arising in quantum information science. Also, we are going to see a recent paper give a tighter instance when I is larger than or equal to 1. So that means because we have known that when I is smaller than 1, we provide a generate solution to solve any problems by one method. However, at least we know that when I is larger than or equal to 1, we know a worst case instance that no any quantum algorithm can do it better. At least for the worst case, we cannot do it better. So that has been, if they are correct, and it seems that we have closed the gap and closed the open problems at the times to know the pretty type, the classifications of the harness of solving problems on computers.
Yeah. A question on this?
Yeah,
so
sure.
Is this result like independent of how the vectors of the differential equation are encoded into quantum states?
Yeah, so I think throughout from this part, and our description is that so we want to produce like given some description, that means like given fault encoding or sparse oracle or some certain state operation oracles, our goal is to provide a quantum state solutions. So I would say we just try to care about how to efficiently do some efficient, solving some nonlinear dynamics and inside computers, and everything should be just we care about our quantum states. Just at this moment is that. Yeah. So we haven't really developed maybe, but towards the end, I will try to discuss if it's sparse enough, you can really efficiently upload or download your data. Yeah, right. So it's pretty good question because it's relevant to the second problem. When you have better understanding of nonlinear, we need to turn your attention to end-to-end. Yeah, yes. I will cover that later. So we are going to see. Oh, sorry.
Could you elaborate on how the this divergence of states leads to the exponential complexity?
Yes. So maybe basically speaking, if you have two potential quantum states file side as your two possible inputs of your nonlinear dynamics, and they are pretty close. I mean, let's say you can really quantize the overlap by maybe 1/1 minus epsilon. That means the overlap is very close to 1, and you can only take a very short time. I mean, logarithm of 1/epsilon is very fast. Algorithm can fast evolution can really try to try to amplify your angle in order to only the two quantities have a constant overlap. I mean, the larger angle means a small overlap. So I mean, you can really change the overlap from 1 minus epsilon to the constant, and with the evolution time is logarithm 1 of epsilon. However, we know the lower bound is at least the 1 over epsilon queries through your certain any protocols, and so that means you cannot solve the problem in a polynomial time. You need to take at least exponential time to solve the problem.
Exponential time to solve the problem. Are you just saying that because of sensitivity, you need like exponential accuracy on your initial state to like correctly follow the state you meant to? Like, is this a space complexity or is this a time? I'm not.
It's a time complexity. Yeah.
Why does it take exponential?
We need to really, first of all, maybe a better the clarification is that the lower bound is for the query complexity, at least how many queries we need for certain protocols, and for the time complexity, because we really transfer your how many times you query your oracles inside your polynomial regions, and that's equivalent to time complexity in some sense. Yeah, thank you. We can discuss offline. So because there are a bunch of many technical details in lab, I'm glad to share many thoughts on that. Yeah. Thank you. Yeah. So after talking about the theoretical size, and maybe I can briefly cover like just a bunch of applications we are glad to see for either classical algorithms or quantity algorithms. Again, many of the results has been carried out in a real device classically. So even sometimes it's not so efficient to do the color minimization, but people are willing to really do that some study, like many applications, and like in biologies and like SEIR models, like I'm not sure we still care about that, but at least moment we care about that at the time. So we care about like how to really efficiently model the transition between the different class of your populations, like suspective, exploitive, infectives and recover popularities. And we also try to apply our techniques to study some control problems, like how to really find your attractors from some systems, like try to find attractors or stationary points from your predictor prey systems or other systems. We also care about the applications of the fluid dynamics and process dynamics, like a bunch of many algorithms use Kalman or Kuhlmann or other linearizations with applications to fluid dynamics. And finally, also some results try to combine uncertainty quantifications with your approach in order to really study can we apply our quantum linearization frameworks toward some applications in the data science, really try to model and govern the express of your uncertainties. So there are a bunch of results. Considering the time, and maybe I just only give one example from our recent work, and again, it's by Dong'an, Difang, Jiasu Wang, Brunholo, Stephen John, and me. So in that paper, and we try to still apply our quantum color minimization to solving the high-dimensional reaction diffusion equations. At least from you can see, this is a linear standard Laplacians. Of course, Constantina has introduced that, so they are working towards a harder problem with fractional case, but just we focus on linear Laplacian operators, and also with a certain potential nonlinearities, like you could try to really plotting your favorite nonlinearities from depends on what's your areas, like from biology or ecology or physics, and there are many different applications as listed here. So for that results, sorry.
Capital D, is that a differential operator or a constant? It might change the problem quite a bit. The capital D. The round in the first line 10. There's a capital D before your Laplacian. Is that a differential operator or a constant?
Just a constant. Would you regard it as a constant? Just a constant prefactor. So it's not the operator.
Because that makes a little bit of a difference, I guess, right?
I totally agree. Just maybe think about it like a constancy. Maybe it's better. I agree. Like if you consider maybe a different design of your case, maybe you can put some time or f dependence of d to become like the time varying parameters, or even you consider some other parameters for the Laplacian operator. It will be harder. So we should choose a d as a positive constant. So this part should still have strictly negative eigenvalues. Yes, pretty great questions. We expect that maybe we can do something more to study more complicated and carefully design the nonlinear PD problems. We are really expanding that. So yeah, great. So for lab problems, and in one word, as summary, is that we develop the efficient quantum algorithm to produce a quantum state corresponding to U, and then we try to study how to post-process U by estimating some ratio of your kinetic energy with some efficient complexity. The efficient means that maybe you take like poly T, poly of spatial dimension D, which D can be assumed to be pretty large. Also, over 1 of epsilon accuracy just can achieve Heisenberg limits, and it's a potential exponential speed up only compared to the classical PD solvers. Maybe I believe maybe if you really try to study some stochastic algorithms or sampling algorithms, maybe it's not a fair comparison, but some classical algorithm can also resolve the curse of linearity to achieve poly D. But as far as right now, I do not really see an exact stochastic algorithm can work on almost the same problems. We expect maybe classical community can really try to really beat our case and try to give another comparable classical sampling algorithm. But as far as I know, even you know how to design some nonlinear sampling algorithm, it's not so easy to really provide some arbitrary estimate of your observable. But it really depends on what's your care about outputs. So also improved analysis from the column linearization also indicates that so maybe gradient flow is a pretty good nonlinear dynamics visual for the zone. The reason is that so maybe you could think about like usually the gradient flow is we try to study some gradient flow towards a certain energy functionals, and it should be steady flows. Usually, you will not directly blow up if you give a good prior estimate. Usually, it should just gradually towards your minimizes. So it sounds like the good targets like with linearization, so we do not really worry about the lower bound case. And actually, in our paper, we really rule out the worst case, the showing in the earlier papers. So that means we can give a better linearization is because we can avoid the butterfly effect, and we can avoid the worst case that we don't want. And it seems that for average case, it was better than the previous result. So it directly indicates some informal, so just the indirect result like how we do the task from the machine learning problem, because we should focus on the study of the gradient flows. So for the second part, before like any questions for first part, or maybe we can just discuss later. Yeah, for secondly, I would like to really share. Yeah. Okay, sure.
So you have discussed very successfully to use your parameter R. I mean, not you, but you also predecessor, right? What's the next parameter to work with if R doesn't work?
If R doesn't work, then I would suggest maybe you can try to consider alternative linearization techniques like pruning or other linearizations. Maybe because Talman is the simplest linearization, but directly try to regard your polynomial nonlinearities as your new variables. But maybe you can consider some other linearization to reformat your nonlinear problem to some easier problems. Maybe you can really make use of some nice linear features from the nonlinearity essentially, but you can see we really do not really try to choose some certain proper-based functions. We only choose polynomial, but I believe for many nonlinear problems, you can choose better base function to do better linearizations. Also, maybe you can consider, so how to prove a better column linearization. I mean, if R doesn't work, you just prove a better convergence radius, and I will be very happy. Yes, thank you. Question?
Curious, what do you mean by the kinetic energy here?
Yes, basically speaking, the kinetic energy, because we consider U as meaning of some gradient flows, and so we just try to estimate like some integrations of L2 known of your gradient of U. So I do not write the formal form in these slides, but I'm using chat in my paper, and so we define what's the kinetic energy, or some people call it like the delivery energy form of this system, and we can really perform the MDTO estimation in order to produce some integral of your L2 known of your gradients of U. Yeah.
Okay, something related to the gradient. So if you represent something like concentration, can you also give like, I don't know, like if I pick a region of the domain, can I know what the concentration is in that region, the total amount of U?
Sorry, what did you mean by concentration? Or
Like U usually represents some kind of concentration.
I do not really think about that from this just direction because I was mainly inspired by some standard PDs from some certain like biology or problems. So maybe you can tell me maybe later about why it has this meaning. Maybe just because I do not have enough knowledge for that.
Sure.
Yeah, sure. Thank you. Yeah.
So what's the heuristic reason that the linearization may work better for gradient flows?
What's the reason?
Sort of that. I mean, what is the?
So just one reason is that we can really rule out the worst case. We can show gradient flow do not, under some conditions, does not admit the worst case appears. We do not, we will not face the really, the terrible, the worst case to face out. So for average case, may better. And suddenly it's about some technical reason. Like when you carry your analysis of column linearization toward this example, this equation, we really figure out like you can do something better error measurement. So that means we can really try to select some better error measurements, also with some better numerical results to indicate I think to be a better case to work. Yeah. Yes, thank you. Yeah. So let's move forward to talk about some machine learning perspective. Yeah. So I would like to show some more maybe fancy pictures in here, and I think people are all pretty excited about the recent the progress arising from the machine learning, or just say like the AGI, I mean the artificial generative intelligence, and so from that part maybe we know it's so powerful that so even really we could not simply imagine in previous years that we can really design some intelligence the chatbot to really change our life, because we can really usually frequently interact with your ChatGPT and return many things that we don't know, and sometimes correct, sometimes wrong. But anyway, we give them some input, they can really tell us some surprising output messages. Also in other areas is called the image generalization. I mean how to generalize some very fantastic images even not appear in our real world, like the least very famous features was just drawn by Dell E3. Dell E3 was just released several weeks ago. It's fancy news. It seems to be a state of the art. The AI, image generalization tools. So for that, are all based on like GPT, maybe GPT-3 or GPT-4. And however, for that task, the cost is less. So we really need some expensive money and some huge produce of the carbon dioxide in order to train some large scale language models. Like this is some data from some literature that we want to train maybe a huge language models with the dimension over the 10 to the 11. It's pretty costly. However, we imagine what's the best way we can train. The best is to achieve the exponential speed rates by computers, right? So we imagine if it's possible to reduce the pretty long training time and resource to be pretty small. I mean, maybe save the 1 month the training time to maybe 0.001 seconds. Is it possible? So really, at least we need to provide some studies from the theoretical side to see how we can do, and at least maybe we can make first step. Yes, I think we can really partially do something, and this is a recent preprint by maybe Junyu, Mingzhao, and me, Ziyu, Yunfei, Yuri, Yan, and Liang, and we study a certain quantum algorithm towards, the quantum algorithm for large-scale machine learning models. This is a simple diagram of what we try. The basic idea is that, so we know there are 2 steps in the training of large language models. One is pre-training and one is fine-tuning. So for pre-training is harder, so we do not do something quantumly for that. Just classically, we have some output from dense neural network. We did pre-training classically, and then we need to do some sparse pruning of your weight parameters to get some sparse in our neural networks. And then we can, so if the connectivity and your data can be sparse enough, it allows us to efficiently upload your data onto your computers. inside quantum computers, we can really try to simulate some training dynamics by linearizations, and then after that, you do some measurement to produce some sparse trend with vectors and to reconstruct your outputs of the sparse neural network. So that means the quantum can contribute to the some stage of your fine-tuning part for some sparse neural networks. Yeah, so there are some theoretical results and some numerical results. Theoretically speaking, I think we are familiar with the complexity, right? Just the statement is that for some sparse and almost dissipated machine learning models, with the definition like the sparsity, size, and the running some iterations, we can really give the point time linearizations with this cause of potential speed up in terms of like the size n, but also depends on sparsity. So we also discussed how to really, do the quantum tomography to produce estimates of some sparse weight vectors. So there are two principal assumptions. One is the sparsity. We're likely to know so in the areas of sort of sparse training, which will maybe a very strong assumption is that we hope the sparsity doesn't scale with the size of the model significantly. And maybe sometimes you will really have scale, but right now we just give this some assumptions. Second is that for the hashing of your gradient dynamics, we need to guarantee like we have most dissipated modes, and that means hashings of your gradient dynamics should have maybe the divergence mode should only have a polylogarithm dependence in terms of a whole numbers of this dissipating modes. A more fine-grained introduction is about structures, and it's a pretty easy way to understand what we did. So we consider given some loss function, input weights, and training set. The standard way is to consider the gradient descent towards your certain loss function. In this example, we consider gradient descent, and we consider MC loss, which is L2 realizations of your like last output layer and with some fitting terms. One example is to consider very standard classical MLP model. For that model, you can see from one layer to the next layer, just we try to perform some nonlinear activation function. For instance, you can choose Liu and multiplying some weight matrix and bias vectors, and then you get the next layer, and you need to repeat again, just nonlinear weight and bias, and all the weight matrix and bias vectors in each layer should be your trainable weights, and it's pretty huge vectors that we consider about. So just the three steps and pretty standard, like we try to upload your data if it's sparse enough. For dance, of course, you can try to pick up some imagine the procedure like you rent. And for training set, just given the quantum state input, we are able to round out some linearization. It's a formation from some probabilistic versions, and we also need to do some truncate linear system to filter out some divergent modes to get a certain solution under some guarantees. Finally, is to carry out some tomography and to download some nearly sparse trend states with all the complexity can be shown depends on your sparsity. Independent of sparsity parameter, it can be a polylogarithm in terms of the size n. So there are some basic framework in here. And we also carried out so many classical experiments. It's because we do not have the powerful enough fault-tolerant computers to carry out, but at least we can examine the new structure of our linearized neural network to work on some real applications. So also, again, it's a contribution independent of quantum computation. So we try to carry out something from small scale to large scale. This is the most simplest example, single hidden layer neural network. For this very small case, we can really examine the error curves decay or some power loss of time to examine. So pretty nice curve to describe how the error scaling. And for larger case, we really try to examine some the performance for real use. I mean, in the CV, the computer visions, we carry out the problem to classify the C400 data set. That means we given a standard ResNet, we need to do the sparse pruning and then do a linearization. And so we pick up the parameter like the phone, like the over 10 to the 6 to the largest case 10 to the 8, pretty large numbers of parameters, and maybe even smaller than the size of a large language model, but still is not so small. And we can really observe some estimate like try to trap the change of the range and the distributions of your special from your hashing. And we also try to observe like this is the error curve. You can see how to really guarantee that some time like you can really approximate well. Also how to guarantee at some before it blows up, we can really know that. So we can really get some the increase of your test accuracy for the task from 0 toward nearly 0.6. And so that means because you to imagine for any methods, for any linearization, the neural network should be super nonlinear. It's ridiculous nonlinear case, and what you can do best, I expect, is like you can only suppress your linearization error in some time interval, but during the interval, like it's the case that quantum can make some potential advantage. That means you can, before you have some guarantee, because you have some guarantee, so you can really, on that region, you can really linearize it well and then solve it well and try to really get a pretty good approximate the weight vector. So for that trend parameter, you can achieve maybe not so good but not so bad test accuracies. What is the nearly 6.7? And maybe just quickly say we really try for some when we increase the shape, it seems that accuracy and it's not so good. It's just only over 0.4. But we really try to discuss how to get some using some cheat in engineering, like download, re-upload, and really try to do the pretty much time in order to raise the accuracy to the 0.6. How good about the 0.6, about 60% accuracy to classify your data. The benchmark of the standard sparse training by the standard ResNet is about 0.7. So maybe not good thing is that we do not really reach the benchmark, but it seems like it's not so bad because we can really exponentially save the time and then to reach nearly benchmark the accuracy. Question?
So on your previous slide, I was curious, do you have any intuition on why the spectrum of your Hessian gives you some metric of your error?
So I think from the perspective of the dissipated OD, you can see when we carry out linearization, dissipation made a lot of work because you can strong dissipation can try to control your nonlinear and other your unwanted terms. So we want the gradient dynamics should also be in some sense should be dissipated. So we try to a little bit revise the condition to be sort of almost dissipated. But we hope you have more number and range of your dissipating modes on your Hessian. So also we can observe that.
We're a little bit behind the schedule. Do you want to maybe wrap it up?
Oh yeah, sure. It's near the end. Yeah. Yes, thank you. So yeah, so just I think just almost last some experience I want to present. Also maybe just for first quickly say that we just informally expand something like the dissipated is coming from the information bottleneck theory, but not a rigorous argument. Just say there are some reason. We want to criticize that quantum neural network have something good or something not so good is because it suffers from numerous settle points and possibly hard to change because it's not dissipating now. So why not choose classical neural network rather than quantum neural network? So it's a story like why we study quantum algorithm for classical neural network instead of variational quantum algorithms. Also, we try to have some informal reason like why we can make it super sparse because the lottery TT hypothesis gives some reasons like if we are lucky enough to construct some winning TT, we can maybe get some comparable sparse sub-network comparable to original dense networks. And so this is a brief summary. I think theoretically we propose the first efficient, maybe that means poly time and polylog and quantum algorithms for training classical neural network. It seems to be the first quantum algorithm for training classical neural networks. Also, and we can really use classical experiment to examine our algorithm to validate the potential advantages by enlarging now the parameter numbers. And some improvements, maybe not, just like how to do the better theoretically or toward applications and many potential terms. Also, there is a pretty short summaries of all my research agenda for quantum for science to contribute to like quantum physics, contribute to neuroscience and data science. In the future, I will carry out the result maybe in several years about like how to do robust or near-term quantum simulations, do the efficient quantum scientific computation, how to carry on the scalable quantum machine learning. So thank you very much.